Hi everyone, welcome back. The learning goal for this video is to be able to write the name and formula for an ionic compound containing a polyatomic ion. An example of an ionic compound containing a polyatomic ion is sodium chloride, and that is used in the processing and bleaching of pulp from wood fibers and recycled cardboard. So what are polyatomic ions? So as the name suggests, poly, they are a group of atoms with an overall charge. They often consist of nonmetals such as phosphorus, sulfur, carbon, or nitrogen and oxygen. They're usually anions, which means that they have a negative charge, typically -1, -2, -3. But there's one exception, ammonium, which has a positive charge. So that's the only cation that's polyatomic, NH4+. Here are some other examples of ionic compounds that contain polyatomic ions. So we will learn that this is sulfate, so calcium sulfate, which is used in this plaster cast. And then here we see an example of fertilizer, ammonium nitrate. So this is a polyatomic ion, and this is also a polyatomic ion. So sometimes you won't see a metal and a nonmetal like you traditionally see with an ionic compound, but we definitely see a cation and an anion, which is why this is still considered an ionic compound, even though it contains nonmetals only. So here is the list of some common polyatomic ions. You are not expected to memorize this for my class. I will provide this table for in-person assessments. So like I said, don't need to memorize it at all. You'll be provided it, but it is important to become familiar with the polyatomic ions. Once again, you're learning the language of chemistry. And so the more you learn it without needing to reference this table, the faster you will master the language of chemistry. So, and that's only through practice. For me, when I was a student, I made flashcards because I had to learn the polyatomic ions. And, you know, there are great tools online as well, or apps that probably can help you with studying your polyatomic ions. But you will have this reference table for assessment, so that takes off some of that pressure. But once again, the more you learn it, the faster you'll get at naming compounds and speaking the language of chemistry. And so, for example, this is hydroxide, which is OH minus. We have the nitrogen series, ammonium, nitrate, nitrite. The chlorine series is perchlorate, chlorate, chlorite, hypochlorite. The carbon series is carbonate, hydrogen carbonate, also known as bicarbonate, either works. Cyanide and acetate. The sulfur series, sulfate, hydrogen sulfate, or bisulfate, either works. Sulfite, hydrogen sulfite, or bisulfite, either works. And phosphorus, phosphate, hydrogen phosphate, dihydrogen phosphate, and phosphite. And note the formulas and the charges are there. Now I just want to highlight some patterns for naming the polyatomic ions. Once again, you don't need to memorize them, but it is helpful to recognize patterns. So for example, names of most common polyatomic ions end in ate. So sulfate, SO42 minus, phosphate, PO43 minus, nitrate, NO3 minus. When a related ion has one less oxygen, its name ends in ite. So more oxygens, 8. And then notice how this one has one less oxygen. So it's not sulfate anymore, it's sulfite. Phosphate turns into phosphite when we have one less oxygen. And nitrate turns into nitrate when we have one less oxygen. Exceptions to these rules are the following: cyanide, hydroxide. So you notice there's no ate or ite there. And then if you have a H plus to a polyatomic ion, you can see here, originally, this is actually the carbonate polyatomic ion. And so if we have H plus, we can call that hydrogen carbonate. And because H plus is a positive charge, +1 - 2 is a -1. So that's where we're adding a +1 to its charge. So this is hydrogen carbonate, also known as bicarbonate. You can use either name. Sulfate plus a hydrogen plus, this one here. Notice how the -2 is now a -1 when we add the H plus. This is hydrogen sulfate, also known as bisulfate. And so here is a halogen, chlorine, that forms 4 polyatomic ions with oxygen. Notice how oxygen's consistent through all these polyatomic ions for the most part, and that's because oxygen is a major component of our air in our atmosphere. So in this case here, each of these has a -1 charge, but the only thing that's changing is the number of oxygens here. And so this is perchlorate, chlorate, chlorite, and hypochlorite. So let's talk about writing formulas for compounds containing polyatomic ions. So we're going to use the same rules of charge balance. Remember, the charge of an ionic compound always needs to be 0. It needs to be neutral. You can set up an algebra equation, or you can strategically use the crisscross rule, which I'll show you. But for example here, magnesium nitrate, you have magnesium is Mg2+, you have nitrate, which is NO3-, so you write the whole formula with its charge. And it looks like we have 1 magnesium with a +2 charge, and then we need 2 nitrates with a -1 charge to balance it out to 0. So when we write the formula with Mg, there's only needs to be 1. You need to put parentheses around the polyatomic ion because those are a group of atoms and they have to stay together. So put parentheses around polyatomics, and then the subscript 2 is outside to indicate that I need 2 nitrate polyatomic ions to balance out the magnesium's +2 charge. Another way to kind of think about this, rather than doing the algebra, like I said, you could do the crisscross rules. So I like to have students just write down the cation and the anion. And then I have them do immediately always put parentheses around the polyatomic ion. You can erase them later if they're not needed. So like I said, I get students in the habit of just putting parentheses around polyatomic ions, because otherwise, if there's no parentheses, then someone might assume it's like 6 oxygens and only 1 nitrogen, and that wouldn't be the correct formula. So put parentheses and then do the crisscross rule. So 1 down by the magnesium and 2 down by outside the parentheses next to the nitrate. So you can still do the crisscross rule, but put parentheses around your polyatomic ions. So let's go through the guidelines for writing formulas with polyatomic ions. As you saw, we identify the cation and polyatomic ion or anion. We balance the charges, or we can do the crisscross rule. And we can write the formula always with the cation first, using the subscripts from the charge balance. So let's do an example together. Let's write the formula for aluminum bicarbonate. So first, aluminum on the periodic table is a metal in group 13, and it has a +3 charge that doesn't change. It's not like a transition metal. So always +3. And then when you see a name that looks different than what we worked with in the previous video, for example, bromide, chloride, nitride, etc., then it's most likely a polyatomic ion. And that's why I said earlier it's important to become familiar with the polyatomic ions so you can recognize when you're working with one. So for example, bicarbonate is not an element on the periodic table. And so we can come up to find that table here. And carbonate is CO3 2-. So we'll want to write the full formula. Oh, actually bicarbonate, my apologies there. We're looking at bicarbonate HCO3-. Okay, so bicarbonate, it could have also been written as hydrogen carbonate, but we're looking for bicarbonate HCO3-. And then write the cation and then the polyatomic ion with parentheses before doing the crisscross rule. Just want to get in the habit of putting parentheses. We can always erase them if they're not needed later, and I'll show you an example when that's the case. So when we do the crisscross rule, the 3 goes down outside the parentheses of the bicarbonate, and the 1 goes down next to the aluminum. So we have 1 and then 3. And that's the formula for aluminum bicarbonate. All right, pause the video, try the study check on your own, and then come back and check your work with me when you're done. All right, let's write the formula for sodium phosphate. So sodium is the cation, and that's on the periodic table as Na in group 1, so that's a +1 cation there. Phosphate, not on the periodic table, must be a polyatomic ion. So we find the table here. We look for phosphate, PO4 3-. So once again, write the elements without the charges and put parentheses around the polyatomic ion before we do the crisscross rule. The 1 goes outside of the phosphate, outside the parentheses, and the 3 goes next to the sodium here. So we have Na3. And this is where you would not need parentheses. So if you put a 1 out here, you only have 1 polyatomic ion, then it's not necessary to have parentheses. So this is where you would need to erase the parentheses. So you could end up, I'll just rewrite it again to bring it a little closer, to end up with Na3PO4. So the only time you need parentheses for polyatomic ions is when you have more than 1. All right, so naming compounds with polyatomic ions. Once again, you first write the positive ion. If it's not ammonium, it's usually a metal then. And then you write the name of the polyatomic ion second. Recognizing those polyatomic ions in a chemical formula helps to name it correctly. You don't need to change the name of the polyatomic ion. You use the name as it's written in the table. And as with other ionic compounds, no prefixes are used. Later on, when we learn about binary covalent compounds, we'll use prefixes to determine the number of atoms. That's not the case here for ionic compounds because there's only one formula since everything has to add up to 0 for each ionic compound. So as you can see in these examples here, we have sodium, the cation, the full name, and then SO4 is a polyatomic ion. So we look it up, it's SO4 2-, so it's sodium sulfate. Don't forget when you have transition metals, like we learned in the previous video, that we need to include Roman numerals for the charge of that transition metal. So we would determine that based on the polyatomic ion. So first we have Fe, we don't know what it is, but phosphate is 3-. So if we set up the algebra, it'd be 1 iron X plus 1 phosphate, which is a -3, adds to 0. X minus 3 is equal to 0, so X is equal to 3. So you can do some algebra utilizing the charge of the polyatomic ion to determine the charge of the transition metal. So this would be iron 3 phosphate. And then last but not least, we have aluminum, and then this CO3 here is carbonate. So aluminum carbonate. Aluminum is not a transition metal, doesn't have variable charge, so we don't need a Roman numeral. Here's some example of compounds that contain polyatomic ions that you may come across in your daily life. So for example, barium sulfates used as a contrast medium for X-rays. Silver nitrate is used as a topical anti-infective. Sodium bicarbonate is used as an antacid. It's also baking soda, so you might bake with it. All right, so let's do a study check. Pause the video, try this on your own, and then check your work with me when you're done. All right, the first one we have is aluminum nitrate. So the first thing you'll want to do is write the formula of the cation, aluminum 3+, and then look up nitrate. And you should have found that nitrate is NO3-. And then write the formula without the charges, putting parentheses around the polyatomic ion. Then you can do the crisscross rule, 1 for aluminum, 3 for nitrate. So the 3 goes outside the nitrate. Then we can see the answer then is C. Copper 2 nitrate, so copper is Cu, and then 2 is the charge. Nitrate, we already have that formula above. And then when you write the formula, Cu, and then put parentheses NO3 without the charges, and then you can do the crisscross rule. 1 comes down for the copper, 2 goes outside the nitrate. So it looks like the answer is B for copper 2 nitrate. The next one, iron 3. Hydroxide's a polyatomic ion, and that's OH-. So once again, write it down first, putting parentheses around the polyatomic ion, and then when you do the crisscross rule, the 3 goes outside the parentheses of the hydroxide, and then 1 for the iron. So your answer is C. And I recommend when you're doing multiple choice problems, especially with naming or with any problem, even an algebra type problem, to work through the problem first before looking at the answers, because sometimes the answers could mislead you. And so try to work on it on your own first, and then see if you can find the answer as part of one of the solutions. Last example here, 10,4 hydroxide. So 10 is Sn, and then 4+ is the charge. Hydroxide is OH-. So I like to write these down first without the charges, but parentheses around the polyatomic ion. And then crisscross rule, the 4 goes down here, the 1 goes down here. And so your answer is A. All right, so here's a guide to naming ionic compounds with polyatomic ions. So once again, identify the cation and polyatomic ion, name the cation, use a Roman numeral if needed for a transition metal, name the polyatomic ion as is, so you can find that on the table, and write the name for the compound, cation first and the polyatomic ion second. Now just something to note, remember there is one polyatomic cation, and that is ammonium. Here's a flow chart that I find really helpful when it comes to naming ionic compounds, because there's different types of ionic compounds. So let's walk through this together. And we're going to focus on this part here, not the molecular part just yet. So ionic, we have a metal and nonmetal, or ammonium, which is still nonmetals, but a cationic in nature because it's positively charged. And if you're looking at the metal, and if it forms only one positive ion, then there's no need for a Roman numeral. You just use the full name of the element, or for example, ammonium, if it's ammonium. If you have a metal that forms more than one positive ion, then you use that element's full name, but you need a Roman numeral equal to the charge. If you have a nonmetal, then you'll want to make sure you can verify if it's monoatomic, so that's derived from the periodic table of elements, or if it's polyatomic, when it's a grouping of atoms there that have an overall charge. If it's monoatomic, then you use the first syllable of the element name followed by IDE. So for example, oxygen, you would keep ox and then put the IDE, so that's oxide. If it's a polyatomic ion, you just use the name of the polyatomic ion as is. And we'll discuss more about molecular, binary compounds in a later video. So go ahead, pause the video, try naming the following ionic compounds, and then check your work with me when you're done. Okay, first things first, let's write down the name of, or identify the ions first. So Ca is calcium, which has a 2+ charge. And then I recognize NO3 as a grouping of atoms. So once again, recognizing that's probably a polyatomic. Let me double check on the table. So if I look for NO3, it's like, yep, NO3 minus, and that is nitrate. I double check that calcium is not a transition metal, so I can just write the name as is, so calcium. And polyatomic ion, once again, you just write the name as it is on the table, so calcium nitrate. All right, the next one, FePO4. So I recognize Fe as a transition metal. So I don't know its charge, so we'll have to figure that one out. And it also helps me recognize I'll need a Roman numeral in the name. PO4, that seems like a grouping of atoms that may be a polyatomic ion. So let's go ahead and use our resource. And indeed, that's phosphate, PO4 3-. So let's write that down. And that's phosphate. So we'll just write that note down real quick here before we forget. And then we will need to do some algebra to figure out what X is, the charge for iron. So looks like there's one iron and there's only one phosphate. So be careful with that. Sometimes I'll see students say 4, but remember the 4 is part of that grouping of atoms. And there's no parentheses, so that implies there's only one phosphate. And that phosphate has a -3 charge. So X minus 3 is equal to 0, so X is 3. So when we write the name, it's iron and then Roman numeral 3 for the charge, and then phosphate for the anion, the polyatomic anion. All right, let's do another study check. Pause the video, try it on your own, and then check your work with me when you're done. Okay, we're going to name each of the following compounds that contain polyatomic ions. I see Mg, which is magnesium. I'm going to write down that cation. It's a +2 charge because it's in group 2. SO3 looks like a grouping of atoms here. Must be a polyatomic ion. Let's check what that could be. So SO3 is a sulfate series. SO3 2-, that's this here, sulfite. So let's write that down. So that's sulfite. Now, because magnesium is not a transition metal, doesn't have variable charge, we just write its full name, no Roman numeral needed, and then sulfite also, its name as is. Now remember, if we had done the crisscross rule to kind of rederive this formula here, you write down magnesium and then put parentheses around the sulfite and then crisscross here, but we need to simplify that. So that's why it turned into MgSO3, because we have to give the simplest whole number ratio of atoms or of ions in an ionic compound. All right, the next one looks pretty similar. So we have magnesium again, the SO4. So definitely a polyatomic ion. Let's look that one up together. So SO4 2- is sulfate. Remember earlier we recognized patterns for some polyatomic ions. If there's the greater number of oxygens ends in 8, one less ends in ite. So that's an example of that pattern there. We're going to write the name magnesium, keep the full name of that cation, and then the anion name, the polyatomic anion name is sulfate. So once again, as we're learning the language of chemistry, if I told you in the lab you're working with magnesium sulfate, with enough practice, you'll be able to visualize, oh, that's MgSO4. Versus if I said, hey, we're working with magnesium sulfite today, that changes the compound you're working with and its properties. All right, last example, Pb, which is lead. And lead is considered one of those elements that has variable charge. So if you look on the periodic table, it's right underneath 10. So even though technically not a transition metal, it is one of those other metals that does have variable charge. So when you determine that, so PO3, let's go ahead and look that up. That looks like a grouping of atoms on the periodic table, not the periodic table, but of the polyatomic ions. PO3, okay, good. So PO3 3- is phosphite. So it has one oxygen less than PO4 3-, which is phosphate. So we have phosphite here. Let's go ahead and write that down. And we'll do some algebra to figure out the charge for lead. So it looks like we have 3 lead ions with unknown charge plus 2 phosphite ions with a -3 charge. Everything has to add up to 0. Let's simplify this algebra equation. So we have 3x minus 6 is equal to 0. I'm going to add 6 to both sides because I'm trying to isolate x. So 3x equals 6. So x is equal to 6 divided by 3, which is 2. So lead must have a 2+ charge. So when we name it, we will write lead and then Roman numeral 2 to indicate the charge of that lead cation. And then the full name of the polyatomic ion, which is phosphite. So lead to phosphite. All right, last study check. Try this one on your own and then check your work with me when you're done. All right. We have Fe2SO43. So it looks like the cation is iron, but once again, we don't know its charge, so we'll put X there. SO4 is a polyatomic ion. That's sulfate. can look that up on the table. So SO4 2 minus. And so we'll write down that name. So it's sulfate. And then if you were to do the, we can see here, you can almost do the reverse crisscross roll if you want, but let's go ahead and do the algebra. There's 2 iron ions. Looks like 3 sulfates, then -2 charge. Everything has to add up to 0 for an ionic compound because it's neutral. Simplify 2x minus 6 is equal to 0. 2x is equal to 6. And then x is equal to 6 divided by 2, which is 3. So iron has a +3 charge. Just writing my notes down here. And so when we write the full name, we write iron and then Roman numeral 3 for the charge, and then sulfate. Let's do B here. We have the barium, so that's Ba, and barium is located on the periodic table in group 2, so it has a +2 charge for its cation. And then we've seen PO3, that was that phosphite from earlier example. And barium is not a transition metal, so we don't need a Roman numeral. So we just write the full name of that cation, and then the anion's name as well. It's a polyatomic ion, so you just write the name as is. So this is barium phosphite. And then part C, we have NiCO3. So Ni is nickel. It is a transition metal. And we don't know its charge. CO3 is one of those grouping of elements, that polyatomic ion. So CO3, if we look it up, it's CO3 2 minus, and that is carbonate. So let's determine the charge of nickel through algebra. It looks like we have 1 nickel atom and we have 1 carbonate. Make sure, once again, you recognize there's no parentheses, so that implies only 1 of that polyatomic ion. It's not 3. The 3 is part of the polyatomic ion's formula, part of its structure. So you do not want 3 carbonates. To be 3 carbonates, you would need parentheses and a 3 outside of it, right? But right now, it looks like we only have 1 carbonate, which has a -2 charge. Everything has to add up to 0 for the neutral ionic compound. Let's go ahead and simplify. X minus 2 is equal to 0, and then X is equal to 2. So the charge for nickel is 2. And we need to indicate that in the name. So nickel, full name there, 2, and then the name of that polyatomic ion, which is carbonate. So nickel 2 carbonate. All right, thank you for watching. And as always, email me with any questions.